And thank you for the symposium organizers for giving me this opportunity. And also, I would like to thank Professor Espinosa for not picking this topic, so I can have an opportunity to talk about Nacre. Actually, this is also his territory, but I touch a little bit. So today, I'm going to talk about structural origins flaw tolerance in Nacre. Actually, the story started several years ago. We received federal funding from the agency asking us to work on single-wall carbon nanotubes. And we used the best recipe to synthesize single-wall carbon nanotubes with a diameter about 1 nanometer, and use the best recipe, at that time we could to disperse single-wall carbon nanotubes to epoxy matrix. And you can see from the fracture surfaces, this 1 weight percent, this is control sample, 3 weight percent, 5 weight percent. And there are a lot of carbon nanotube bundles. Here, if you look at this carbon nanotube bundle, the diameter is about 500 nanometers. That means inside this bundle, there are thousands of carbon nanotubes. Only the outlayer carbon nanotubes, well bonded with the matrix, truly carry the load, do the work. And the other carbon nanotubes in the core, they are defects. You see, although we saw the pulling out, bridging effects, but when you try to increase the carbon nanotube content from 1 weight percent to 3 weight percent, you can see they tend to agglomerate to form carbon nanotube bundle blocks. And theoretically, if you use rule of mixture MP model, HT model, and you can see by adding just 5 weight percent single-wall carbon nanotubes, and theoretically, you can achieve about 12 times increase in stiffness. But if you do the literature survey, you can see, including my group, and we cannot achieve that 12 times increase in strength, and only about a 2 times increase in stiffness when you add 5 weight percent single-wall carbon nanotubes. So we got to meet our milestones we proposed to the funding agency after the first year, and then we say, well, we turn our attention to nanoclays, because at that time carbon nanotubes were expensive. So we use MMT clay with a thickness about 1 nanometer and edge length about 60 to 800 nanometers, and try to disperse them in agarose matrix. And we tried to mimic Nacre's structure, the brick mortar structure. I'm going to bring it up in the next slide. But we could not disperse them uniformly, okay, in the matrix. And you can see one clay has a thickness about 1 nanometer. And this is the transmission electron microscope of a composite. You can see those clay blocks, they stack together, okay, to form a bigger clay block with a thickness about 13 nanometers. That means in that clay block, there are 13 clays stacked together. Only the top and bottom clays, they are truly bonded with the matrix material. Although we saw if you increase clay content from 0, for example, this control sample, to 30, 60, 80 weight percent, we did see increase in strength. But the trade-off is, you can see the tremendous decrease in ductility. This is not what we proposed to the funding agency. We proposed we add a small fraction of reinforcements. We can achieve simultaneously both strength increase and toughness increase, okay? So very much frustrated, but we have to move on to report to the funding agency. So we turned our attention to Nacre, and this is red abalone shell with this kind of brick mortar structure. And the thickness of those bricks or tablets, okay, platelets, is about 300 to 400 nanometers. And somehow stack them together into this kind of brick mortar structure by organic biopolymer. Those bricks, they are aragonite called the mineral form of calcium carbonate, just like this chalk, okay? It's very brittle, but somehow Mother Nature assembled them into this kind of brick mortar structure. This structure can achieve several times increase in strength and some thousandfold increase in toughness. It's not fracture toughness, it's work of fracture. So we thought we knew the recipe, okay? And you have brittle material. You stack them together using the biopolymer, or use the polymer material, and you can achieve Mother Nature's performance. But we tried, but we failed. Actually, we could not achieve Mother Nature's performance by simply mimicking this brick mortar structure. And then, we asked, why don't the currently used Nacre-like material work? And the second question is, do we truly know the secret recipe for fabricating, Nacre-like materials? We know Nacre actually is nature's body armor. It's very strong and tough. And we thought we knew the secret recipe, the brick mortar structure. And if you can find, brick material like, alumina, silicon carbide to replicate, aragonite platelets, and using the polymer or soft metal material as biopolymer to assemble them together into this kind of brick mortar structure. But we could not achieve simultaneously, increase in strength and increase in toughness. And then I asked myself, am I a good student? Have we learned the true lessons from Mother Nature? So we need to dig out the secret recipe behind this brick mortar structure. And then, you see here is the cell of red abalone. If you look at the cross section, you see this kind of brick mortar structure, those with a lot of bricks stacked together. And from the top view, you can see this polygonal shape, with the edge length about several microns. People thought previously those bricks are single crystals. They're brittle. The high strength and toughness actually resulting from the crack deflection along the weak biopolymer interface. And we use atomic force microscope, soft cantilever, self-tuned. You cannot use auto-tune. Look at the cross-section. You can see those bricks stacked together. But if you blew this area up and to see individual bricks, you can see those individual bricks. They are not single crystals. Inside this brick, there are tons of nanoparticles with a size about 30 nanometers or below. Literally, that time, Professor Huajing Gao, he published a paper in PNAS saying that if you have a composite material with a basic building block size about 30 nanometers or less, that material is going to be insensitive to flaw. So we found this material, and we submit the paper to Nanoletters, and we got the tough review comments back, asking us, well, your finding is very much against traditional thought. You need to provide the second evidence. So my student look at this tile, brick from the top view, and then zoom in, blew it up. You can see 30 nanometer nanoparticles. Although we saw from the fracture surface those bricks, and from the fracture surface, and you see this is the brick surface, there are a lot of surface nanoasperities, like Xiaodong discovered, say, well, those surface nanoasperities actually can work as interlocks against neighboring bricks sliding, contributing significantly to the strength increase and in particular toughness increase. And you can see 5 volume percent biopolymer plays a very important role, not only assemble them together, but also this viscoelastic property of biopolymer can absorb energy. So we say, well, we can propose there are multiple mechanisms work together and push the strength and toughness to the very record high value for this Nacre material. And with all the excitements about our discovery and the paper published in Nanoletters, and my student, very exciting, he encouraged a lot, try to move on. He used transmission electron microscope, look at the Nacre sample, and then at a weekly meeting, he reported to me, he said, well, Dr. Li, well, we published something wrong. I said, well, we already published that paper in Nanoletters. We cannot, withdraw that paper, And he said, well, from the transmission electron microscope, you can see those bricks, they are single crystals. But why you saw previously in this paper, using the AFM tapping mode, you can see there are tons of nanoparticles. But from the TEM, you can see those bricks, they are single crystal. This is a single crystal diffraction pattern. Literally, okay, very lucky. University of South Carolina, my previous university, bought the HRTM, and we look at this brick, and if you select the entire area, you can see this diffraction pattern is single crystal. Okay, a recognized single crystal, 100. But if you zoom in, pick B, frame B, and you zoom it up, and you can see this is one particle with the lattice orientation, that's 100. And if you move this frame to C, you see another particle with different crystal orientation, with the orientation that's 110. If you move this frame to D, area D, you can see another nanoparticle with a different orientation, that's 2R1. And you may say, how about in between this particle and this particle? What it is? You can pick a small frame and blow it up and do the FFT. You can see, wow, this is amorphous. That means there are a lot of nanoparticles. And Mother Nature uses a hierarchical, that kind of secret recipe, assemble those particles together into individual bricks. But if you look at diffraction pattern, this is 100, 1 bar 0, 2 bar 1, you overlap them together. It's tend to be a single crystal diffraction pattern is 100. So actually, Mother Nature hides the secret recipe. Okay, so confuses us a lot. Confuses us a lot. And then you may say, well, 5 volumers percent, biopolymer. And how can assemble those bricks together and nanoparticles together? If the biopolymer is not sufficient enough, okay, it's not sufficient, okay, what Mother Nature going to do? Because we could not see any particle agglomeration, okay? Mother Nature already solved this problem, can disperse those nanoparticles 95%, okay, uniformly, no problem. And if you see this is one brick, this is another brick. And you see here, this is the frame, you blew this up, you can see this is the one particle. This seems like another particle, but with a little bit tilt orientation. But if you do FFT, you can see this actually is a screw dislocation. We know screw dislocation is much lower energy compared with the edge dislocation. So Mother Nature uses another mechanism that's called screw dislocation in assembling those particles from bottom up. All right, I'm sorry. Push the wrong button. And then if you look at individual bricks, you can see this is a mineral brick. And we found, if you blew this area up, we found another particle, okay? And this particle, okay, absorbed from the seawater, okay, reoriented itself, attached to the nanoparticle assembled aragonite, and try to form the pseudo single crystal structure. And this pseudo single crystal structure has a special purpose to against the foreign attacks, okay? And we'll talk about that later. So Nacre is super smart, okay, super smart. And how Nacre assembled those nanoparticles without having the agglomeration. Okay, so we try to disperse carbon nanotubes. We try to disperse nanoclays. We encounter the big problem that's agglomeration, right? Actually, we found, just like a bird has a pre-designed pattern to build the net. Okay? Nacre, Mother Nature uses a pre-designed pattern. You can see this particle, okay, another particle, And they follow this pre-designed pattern to assemble those particles into this polygonal shape, layer by layer by layer. Okay? You say, why? I don't know. Okay? But Mother Nature uses a pre-designed disperse pattern. Solve this problem. Can disperse 95% nanoparticles in 5 volume percent polymer matrix. No problem. No agglomeration. Okay? And people thought previously those bricks are single crystals. And the major mechanism for strength increase and toughness enhancement is the crack deflection. So you can see from the fracture surface, okay? And here is if you make a Vickers indentation, and this is crack deflection. And if you look at the crack deflection, and you can see the crack, those bricks, they squeeze in, squeeze out. And the surface nanoasperities squeeze out. That means those surface nanoasperities serve as interlocks against neighboring bricks, sliding. Interesting, we found, you see here is one brick, another brick, this is crack tip. And when the crack propagate, and you see this crack, actually this brick deformed, plastic deformed. This will reduce the crack tip radius. So the crack tip got blocked. Tremendously reduced the stress concentration in front of the crack tip. That will increase the strength, and in particular, contributing significantly to the toughness of nacre material. And we thought, well, there are multiple toughening mechanisms. And my student, he was very aggressive. He said, Doctor, we need to write a review paper. And then we asked our modelers, try to say, well, can we achieve 1,000 times increase in toughness if we put all the mechanisms together? And the modelers say, well, no, you cannot achieve that. So there must be some mechanism still missing. And try to verify those individual bricks, okay? They are not brittle. So we use a high-citron indenter in the individual bricks. And we saw piling up at around the indentation mark, means they are deformable like metals. And then we use this homemade nanomechanical tester integrated with DI3100 atomic force microscope. Fabricate this dog bone-like sample from Nacre and perform tensile bending or experiments, okay, without electron beam irradiation. And if you see, here is Nacre sample. And here we created a notch, perform 3-point bending, okay? Very interesting. We stretch it, and you can see this is one brick, this is another brick. In between, you have a lot of polymer strands. And then we use AFM to bend individual strands. And we can see there are two slopes, okay? Like you bend a metallic wire. And one slope, this is false deflection, there another slope. That means, oh, those biopolymer strands have the string hardening can strengthen itself during deformation. Okay, so you stretch a rubber band, you're supposed to see, elastic deformation, and not that much plastic deformation if you want to see the fully recovery. Here, if you focus on just this polymer strand, you use AFM, perform 3-point bending, get this force deflection curve, and then you bend, okay, the same polymer strand, get the second curve, the third curve. If you compare these three images, you can see this biopolymer strand getting bigger and bigger and bigger. This gives us a hint. Actually, Mother Nature uses the biopolymer nanowires, okay? Wind up to form coil spring. So we use the coil spring model while explain the force deflection curve, why there are two slopes, why you can see deformation strengthening during the deformation, okay? So that's another mechanism people didn't realize. People say, well, biopolymer, just the wick size, provide the crack path for a crack deflection. Another interesting finding is when you perform 3-point bending or tensile inside AFM using tapping mode, You can see this is one brick. And inside this brick, there are a lot of nanoparticles with a size about 30 nanometer. And we know if you perform tensile test, a rubber band, you see elongation along this direction, right? And you see delta L, right? And this direction, you will see what? Contraction or called shrinkage. And that's delta Z. And delta Z over delta L, you put negative sign, and that's called Poisson's ratio. And normally, you see the positive Poisson's ratio. You haven't heard any negative Poisson's ratio. When my student performed tensile tests or bending using AFM and focus on individual bricks, you can see this is the width, this is the L over L naught, increases. That means you perform tensile, you see elongation along this direction, and you see expansion along this lateral direction. So we got negative Poisson's ratio. And if you look at individual particles, you can see those particles actually, when you deform Nacre, and those particles, they rotate. And this rotation requires increase in spacing between the particles. That is biopolymer increasing in spacing. And to convince the editor and reviewer, and here you see this is one brick, and you perform tensile or bending, and you give the string along this direction. You blow this area up. You can see if you focus on zone 1 or zone 2, focus on a couple of particles, you can see those particles, they rotate in 3D manner. This rotation absorbs a lot of energy, contributing significantly to the toughness enhancement in Nacre. All right, another interesting finding recently we published in scientific reports. People saw those bricks, they are brittle, and cracks peak the weak size. These are biopolymer interlayers, so can deflect it. So cracks are not going to go propagate into individual bricks. So we performed 3-point bending. Here's the Nacre sample, and we created a notch. And you can see, very interesting, the crack deflection. And when the stress is high enough, and the deflection along the biopolymer layer is difficult, actually crack jump into individual bricks. So you see this is a crack path in a zigzag manner along the particle interface or the biopolymer layer inside individual bricks. That means Mother Nature designed multi-scale hierarchically structure at different scale. Okay, you have interlayer, okay, between different bricks. And you have biopolymer inside the bricks between the nanoparticles. So you can see, actually, those bricks deformable and also contribute a lot to the strength, in particular toughness, because you see transplate fracture. You may say, is that true? And try to provide the second evidence. We used a cube corner indenter inside AFM, and we found one brick, polygonal shape, perform indentation, okay, and generate a crack inside this brick. And you see the crack propagation. This is zigzag crack path, and we use FIB to cut this crack, and then we look at the crack path inside HRTEM. You can see this is one nanoparticle, another nanoparticle, another nanoparticle. So this kind of transplatelet fracture is new mechanism. Okay, actually there are multiple fracture enhancement of toughness enhancement mechanism at different levels hierarchically. And you may say, well, how about single crystal? And can you find aragonite single crystal? Okay, this is single crystal. And we use XRD, got the orientation, and then we use Vickers indenter, create a crack from the corner of the indenter tip. We can see this crack, this 200 nanometer scale bar, is very straight. And then we use FIB to find this crack from this orientation, and this orientation, this is another slip system, and then you blew it up, you can see atomically straight. smooth crack path. So this is totally different from the crack path we saw in Nacre, okay, the zigzag fashion. All right, very interesting. We know Nacre actually is nature's armor. And the major function is to protect the soft body against, okay, the foreign attacks in deep sea water, right? If you do the compression test and hydrostatically, and you see Nacre responses very gently, okay, with the fracture strength about 150 megapascal. But if you use gas gun to shoot Nacre sample, Nacre responses, okay, using different mechanisms, I will tell you, and with a fracture strength about 3 times higher than the hydrostatically you compress them. So Nacre is much stronger under dynamic loading, okay, about 3 times stronger than than you shoot it using the hydrostatic compression. So what kind of new mechanisms Nacre trigger and the dynamic loading? And we found the first one is called partial dislocation. We know those nanoparticles, 30 nanometer, it's very difficult to develop full dislocations. So Nacre is smart. Use a partial dislocation and try to let those individual particles, okay, deform. And another mechanism, actually is a hot topic we found, is called deformation twinning. People talk about deformation twinning in nanostructure, engineered nanostructured materials. We can see Mother Nature uses this mechanism, okay, already in nature's body armor. Okay. And then how to apply the principle we learned from Mother Nature to our composites. And one mechanism is called interlocking mechanism. Okay, Xiaodong published this paper in GMR 2001. And then we did experiment and used the AFM, try to pull out those individual breaks. You can see those surface nanoasparates serve as interlocks against neighboring breaks. And generally, if you listen to chemists, what they told you, they pretty much say, well, you create strong bonding, okay, interface between the fiber or carbon nanotube with the matrix. And I ask myself, as a mechanical engineer, what roles I can play in constructing robust nanocomposite material. So we learn from Mother Nature. So we decorate those nanofibers, nanowires with beads, and to realize interlocking mechanism with interlocking with the matrix and interlocking between the individual nano necklaces. So we synthesized boron nanowires. We know boron is the neighbor of carbon in the periodic table, lightweight, strong, and we use silicon oxide to decorate boron nanowires to realize nano necklaces. And then we use this nanomanipulator, perform tensile bending, and to test the individual boron nanowire mechanical properties. And here, you can see the role we can play as a mechanical engineer. Doesn't mean I have any bias on chemists, okay? And we need to work together, try to enhance the properties. If you use carbon nanotube, 1 weight %, single wall, okay? And try to use the recipe I used, okay? And you can achieve about the strength increase 8% in hardness, okay, 12% increase in stiffness. But if you just use half weight % nano necklaces, this is half weight %, this is 1 weight %. You can see you increase strength about 32%. That is 4 times better than carbon nanotubes because you used interlocking mechanism. And stiffness, 62% increase, 4 times better than the 1 weight % carbon nanotubes. All right, so I try to summarize. So basic building blocks in Nacre are about 30 nanometer, those nanoparticles. The individual breaks, they are not brittle, they are ductile. And nanoparticles, they can rotate, deform, absorbing energy, contributing significantly to the toughness of Nacre. Nacre triggers new deformation mechanisms upon dynamic loading. Nano necklaces are much better than single than fibers, okay, like carbon nanotubes in terms of reinforcing effects. And the last one is there are still a lot we need to learn from Mother Nature, and I would like to acknowledge the funding agencies for their support for the projects around the Nacre, this very interesting material. Thank you for your attention. Yes.
Going back to this issue that Gabo was saying, that because when you decrease the size scale, you become insensitive to defects. What is your reading of that? Do you agree with that, or
see here? Yeah. See here. I try to borrow his stuff and your stuff. The thing is here, Nacre's design is hierarchical, multi-scale structure, and between those nanoparticles, there are biopolymer layers. And when you have stress concentration, and this 3D network biopolymer can distribute stress concentration far away from the crack tip. So actually reduce the crack stress concentration. So I think that's the beauty. And for 30 nanometer, but I say, well, you need to have either green boundary, just like they published a paper in Nanoletters about the nano-structured material with a lot of green boundaries. And green boundary can help to reduce the stress concentration. And there are green boundary sliding.
I see what you mean, but I thought his theory is that a brittle material below a certain scale is not brittle anymore. You're showing me that this is inherently not brittle anymore.
I think those individual particles, they are deformable. Although, if you see this chalk material, and the bulk material is very brittle. But when you reduce to the small size, just like silicon, silicon is a brittle material. But if you see silicon nanowire, it's ductile. I think the beauty of nanostructure is they give you the properties, and it's unpredictable. And sometimes it's good, sometimes it's not good. But if you can tailor and use the advantages of those properties, we can build better materials.
Thank you again.
Thank you.